And now it's time for Egg Geek Speak with
GK Technologies,
Sarah and Jody.
In the fields again, I just can't wait to get in the fields again. The life I love is spreading potash for my friends, and I can't wait to get in the fields again. No, I can't wait to get in the fields again.
Welcome back to Egg Geek Speak. And this week we have a very special guest with us today, Professor Emeritus from NDSU, Dr. Goos. He actually was also my major professor when I got my master's degree in soils. So he put up with me the whole time, and I really appreciated it. It was a great experience. And so super excited to have you on. Yeah, so thanks for being here.
Thank you, Dr. Goos.
Let's talk a little bit. You retired from NDSU not so long ago, but let's talk about where you began and how you got interested in soils and led you to getting into soils.
Well, I was a farm boy in western Iowa, and in high school I loved all of my science classes: earth science, biology, chemistry, and physics. I liked all of them. And I was also a farm boy. And when I went to college, I've thought about this, and I guess I came to soil science because it was one discipline that used all of those: earth science, biology, chemistry, and physics. And so it was an intersection of all of those. And like many who find a career in soil science, I had a very good intro soil science class in college. So I think that was one thing that directed me that direction.
And luckily for many students at NDSU too, they also had a very good Introduction to Soils professor, and you as the teacher of Soils 10 for many years.
I enjoyed teaching that class a great deal.
So Dr. Goos had all of these great strengths at NDSU that I remember. Teaching, one of his greatest attributes. I was fortunate enough that when I was an undergrad, I actually got to take soil fertility from him. And then when I came back to NDSU, also got to take Intro to Soils 210. And it didn't matter which subject I took. You were very good at bringing it to life, making it real, getting us into the depths of the theory of why things work, but also making it extremely practical. And so it was just one of my fondest memories. I would have never have gone into soils for a master's degree if it wouldn't have been for that soil fertility class all of those years ago. This might be a little bit out of order, but what was one of your favorite things that you remember teaching your students?
Well, when I was teaching soil fertility and fertilizers, I realized that, not many soil fertility textbooks also teach fertilizer technology. And so I taught not only, the fertility in the soil, but I also had labs on fertilizer technology. And I liked teaching that quite a bit. As far as intro soils, I really did like teaching the podology part of it, the first third of the class. Just like the antenna is a part of an insect, what are the parts of the soil, the various soil horizons? I really enjoyed that part of the teaching it as well.
One of the things when you were teaching the podology portion, I can remember that you spent all of this time driving throughout North Dakota to go and get pet-ons from different areas of North Dakota, really to help show the differences of North Dakota soils. I'm trying to remember, what were all the locations? There was Streeter.
Yeah. So the way the labs were set up, there were 8 stations in each lab, and there were 8 different soils from North Dakota represented in the lab. There was a sandy sandstone soil from Dickinson. There was a clay pan soil from Hettinger. There was from Streeter, it was Outwash. From Langdon, it was Salty. From the Red River Valley, it was high water table. And then there was a normal soil from Carrington. So,
congratulations, Carrington, on your normal soil.
Normal soil from Carrington.
So interesting to think about what we do in precision agriculture all of the time and how these different soils all over can really affect how we see differences across the landscape. And actually see that in your class and have it brought to life was pretty fun.
It's been over 10 years since it's been 10 plus years since I took Dr. Goose's class. But I remember that we had a Prosper soil that my lab partner and I worked on to do our final presentation on.
Well, pedology was always really important to me. When I was an undergraduate in the summer of 1975, I went to South Dakota State University, and I spent the summer in Mitchell, South Dakota. And I had the entire summer being trained in soil mapping by Warren F. Johnson, who was the legend of soil survey in South Dakota. So I had about as good a training in field pedology as a person could get. And you asked me what my favorite soil series is.
Yes.
Well, I don't have a favorite soil series, but I do have a favorite soil horizon. And since this is Ag Geek Speak, and since this has to do a lot with precision ag, I do want to talk about my favorite soil horizon. My favorite soil horizon is whatever comes immediately after the A horizon. Because if you're on fairly level ground, in North Dakota, A horizons all look about the same. But it's what comes next that tells the whole story. I mean, for example, if you're on level ground and the A horizon is followed by the parent material, you're on a floodplain. You're on the floodplain of a creek or a river. If the A horizon is followed by a soil that fizzes, a BK horizon, well, you're on a soil with a high water table. You might have IDC, and you're going to need sump pumps for your basement. If the A horizon is followed by what they call an E horizon, well, in eastern North Dakota, that means you're in a pothole, and the government ain't going to let you drain it. If you're in southwestern North Dakota and you have an A horizon followed by probably a narrow E horizon, you're on a wicked clay pan, and that's a nasty soil, and so on. If the A horizon is followed by a clay pan, you've got a clay pan. And then, like we were talking about at Carrington, if the A horizon is followed by what we call a cambic or a BW horizon, everything is nice. So I have a favorite soil horizon, and that's basically what comes after the A horizon.
I love that. I love that so much. And backing up a little bit, can you explain to us again, like, what are the main soil horizons and what in general they mean? Yeah.
Well, in soil science as a whole, there are 5 master horizons. The O horizon, you're either in a peat bog or you're the layer on a forest soil. You got the A horizon. We know what an A horizon is, the top soil. There can be an E horizon. In forest soils, those are very common. That's a leached out horizon. But in prairies, that generally means you're in somewhere that collects water. And the B horizon, can be almost anything. And then you got the parent material. So those are your basic horizons. But the complexity of the soil is in the B horizon normally.
Did you teach us in class the way to remember the horizons? Is it only apes eat
Yes, only apes eat bananas constantly. Yes, OAEBC.
OAEBC.
I would have that as my license plate, but nobody would know what it meant. So,
I don't remember that, but I do remember that E is the middle of the Oreo cookie.
The E is the middle of the Oreo cookie. In a prairie soil, if you have an Oreo cookie with a black A horizon and a dark B horizon, and the E is the middle of the Oreo cookie, and you're in a pothole and the government ain't going to let you drain it. So,
Are there soil series that are defined as that series because they have that E horizon?
Oh yeah. The Tonka soil in North Dakota and the Tetonka soil in South Dakota are the 2 most common in this area.
That's really helpful to know and remember, I think. Thinking about, like, if you're coming across or you're looking across at a soil series map, if you see that, that's most likely someplace that's constantly
Tonka
wet.
and Tetonka. Yeah, pedology, you could, I guess this is Ag Geek Speak, so that we can geek out on soil horizons.
We can geek out on anything we want. That's the whole point.
Well, anyway, but yeah, pedology is important. And, I'm not being critical in the sense that I'm glad that the tech schools and the colleges are having majors in precision ag. But what varies across the field? Does the sunshine vary across the field? The rain may be a little bit, but not predictably, but it's the soil that varies across the field. There really needs to be curriculum development with regards to soil variability and with regards to precision ag. I think that needs to be developed.
It's interesting that you bring that up, Dr. Goos, because I feel like that's actually something that Jody and I talk about all of the time. How do you look across a field and how do you think about how that field is acting? And is it topography? Well, topography is part of it, but it's not all of it. Is it soil texture? Well, yes, but it's the whole of everything.
In confirmation, we learned the 10 commandments, but in soil science, we got the 5 soil forming factors. And if you dig a hole here and you go 10 steps and you dig a hole there and it's a different soil, we have a very coherent way of thinking about it. What varied? Are you on a different landscape position? Are you on a different parent material? Usually you're not under a different native vegetation, although in parts of Minnesota in the same field, you can go from prairie to forest and it's all been cleared. And so that's not guaranteed either here in northern Minnesota. So the 5 soil forming factors are our mental checklist as you go across a field and see different kinds of soils.
Are you referring to chlorpt?
Chlorpt, yeah.
Okay.
Climate,
relief.
Yes.
Climate,
time,
living organisms.
Yep.
Relief,
time.
Yep. In time, yeah. Not time, not topography. Relief is the topography, and then T is time.
Yep, that's right.
There it is.
Yeah.
I'm glad I gave you good grades in soils.
Secret, we talked to Tom DeSutter last week about chlorpt, so we did have a little bit of a cheating refreshment here. Okay, so you mentioned that you worked with Warren Johnson, the legend of
soil mapping in South Dakota.
Mapping in South Dakota.
Yeah.
When you did your graduate work at South Dakota State, was that related to your graduate work?
No, I was offered an assistantship in pedology, but no, I worked with soil fertility and I worked with soybean fertility as my master's. And then my PhD, I went to Colorado State and I worked with wheat fertility. And so it was just, I don't know why I chose one or another, just the opportunities were there. And then when I graduated from graduate school at Colorado State, how did I end up at NDSU? Well, I basically had 3 offers. This was a traditional land grant college, and it was within 3 or 4 hours of my wife's family, so it was a logical choice. And NDSU was certainly very good to me for 42 years, so yeah, it was a good career. And a good place to work. We have very good experiment farms. And I think that was another big strength of the NDSU system.
You've done a lot of different soils research throughout the entire state of North Dakota in your time. What were some of your most memorable research projects that you've done over your careers?
Well, it kind of evolved. You have to remember, in 1980, when I walked on the NDSU campus, a peanut farmer was the president of the United States. And the number 2 crop of North Dakota, it wasn't barley and it wasn't sunflowers. It was cultivated summer fallow. We had 3 million acres of cultivated summer fallow. Almost the western half of the state was almost entirely wheat and summer fallow, with horrible effects on the soil health and saline seeps. And so my first charge was just to develop nitrogen recommendations for the western part of the state. And things evolved from there. I worked with chloride fertilization and plant diseases. I worked with urease and nitrification inhibitors. And then I worked with phosphorus and on wheat. And then later in my last half of my career, I worked with iron deficiency chlorosis. Ted Helms, I thank Ted a lot, our soybean breeder. The soybeans were coming in and in the late 90s, and the chlorosis was a problem. And so I started working on that. Fortunately, my professor of soil chemistry at Colorado State was Willard Lindsay, who came up with the DTPA soil test that everyone uses. And we just had, phenomenal education with regards to micronutrient chemistry as well. So that was, that fit pretty well. So I ended up with IDC. And I should say that my research career isn't over. I do have a small lab with a couple growth chambers, and I'm still evaluating iron fertilizers for companies. Companies come up with iron fertilizers. They know how to get a hold of me. I've done some variety screening for the food grade industry and so on. So I'm still involved with iron chlorosis research. I know how to screen things, either fertilizers or varieties under controlled conditions, and people are still asking me to do it.
It's important to note that, especially when it comes to iron chlorosis research, inducing a controlled, consistent IDC in a greenhouse, iron chlorotics plant, to a point where you can actually do some good demonstration, that's not easy to do.
It took a lot of work to get the procedures down. That's true. The problem with iron is there is so much of it in the soil. Soil's 4%, 40,000 parts per million of iron. The root zone of a soybean plant probably has hundreds of thousands of pounds of iron, and a little plant will die because of the lack of a few grams per acre of it. There is so much iron in the soil, and the plant needs so little that it's easy to get it wrong. And the plant either is totally green or totally dead. But it took a while to figure that out. I'm just glad to help the fertilizer and the seed industry in that regard, because I really don't know of many people in the United States that can actually do that. A lot of people work with iron, get frustrated, and move on.
I mean, we've talked about this before. I mean, any sort of long-term research or sustained in one single area, specifically in production agriculture, I think is something you don't see very often because the funding sources, it's just the nature of research. It's very hard to do long-term anything.
Well, maybe I was lucky because I had such a heavy teaching load that, I wasn't expected to have a laboratory with 6 graduate students and things like that. I wasn't expected to get a multi-million-dollar NSF grant. The 5-digit figure I got from every year from the Soybean Council was plenty. And, and I thank them a lot too. They still see the value in that work. I mean, there's 2 kinds of problems on the farm, right? There's the problem the farmer knows about, and there's a problem the neighbors know about too. And when your whole field turns yellow, the neighbors know about it too. So, yeah.
And before we talk, I think we can spend a lot of time talking about IDC and some things that we can do to address that on the precision ag world, or precision ag level. I'm curious. So you mentioned chloride before.
Yeah.
And I think most places outside of the Northern Great Plains, when they think of chloride, they think of it as being a problem if there's too much of it, right? Like in the South, they breed soybeans to have chloride exclusion, right? To make sure that they're not getting chloride toxicity. But here in North Dakota, we do test our soils for chloride because we need to know for small grains. Can we talk about your research? I mean, was that due to the research that you did?
Chloride comes from the rainfall, from ocean aerosols. In North Dakota and eastern Montana, when you think about it, I can't know, in round numbers, we're 1,500 miles from the Pacific Ocean. We're 1,500 miles from the Gulf of Mexico. We're 1,500 miles from the Atlantic Ocean. We're 1,500 miles from Hudson Bay. We're a long ways from salt water, about as far as you can get. And we have essentially no chloride in our rainfall. And so if you have a soil that's leached out, where the salts have been leached, back in the 80s, you could find soils with almost no detectable chloride in them. And chloride is a true micronutrient. And there was all this work in the 50s and 60s at NDSU. They would put 15 pounds of K2O as potassium chloride, with barley, and they almost always got plumper kernels, 5 or 10% more yield. And there's no reason for that based on potassium, because there's no starter effect on potassium. Plants have no trouble getting potassium. And so, about that time I started on that in the early 80s, they were showing chloride responses in the Pacific Northwest. Tom Jackson at Washington. So it was just a logical thing to try it here. But, it's much less of a problem now because they're throwing a little bit of potash pretty much into everything now. And it doesn't take much. But back then, these farmers were planting wheat on summer fallow, using 50 pounds of starter and a spray of 2,4-D amine and calling it good. That was farming, right? So to come out and say, we need some chloride, it was a radical idea at the time.
To a certain extent, it is still a little bit radical today, but yet at the same time, it's one of those things on a soil test, especially for small grains, I pull all the time for my growers. And I'll watch that test. Yeah. And there are certain situations, especially in the last couple of years, we've had some barley markets that were pretty valuable. And so making sure that we had that chloride dialed in on that valuable barley at the time was really important. And so I would make that recommendation for those growers.
And these were never full-blown deficiencies, but they did have full-blown chloride deficiencies in eastern Montana. Rick Engel showed that you actually got the true textbook chloride deficiency symptoms in eastern Montana and so on. But again, I think it's less of a problem now because the farmers, the dealers are putting in some potash in with their starter mixtures or whatever.
Thinking about eastern Montana, right? I mean, out of all the areas of North Dakota, Minnesota, South Dakota, eastern Montana probably has the highest, I think, still like residual amount of potash or potassium, right?
So off the charts.
There's really not a whole lot of reason to be putting out that potash when you've got 600 ppm of potassium.
Yeah, and Earl Skogley, my counterpart in eastern Montana back in the 80s, I mean, he was showing, he called them potash responses, but they were to potassium chloride. So the history was there. It was just figuring out what it was from. But in a way, it's a distinction without a difference because if you need chloride, you're going to use potash, right? So potassium chloride, yeah.
That's really cool. And it's such an important piece of North Dakota fertility.
Do you know of anybody else that's really worked on chloride to that level where we really...
Well, the three people who worked on it the most were Rick Engel in Montana, me in North Dakota, and Paul Fixon in South Dakota before he went with the Phosphate and Potash Institute. Yeah, I think the three of us pretty much nailed down that we needed it. Rick on wheat, mostly on barley, and Paul on wheat as well.
Can we geek out for a second on like the mechanism of like what is going on like when we don't have that chloride there? Is it?
Well, okay. It is a true micronutrient. It is a nutrient. You can actually get deficiency symptoms of it, and they had those in Montana. I wasn't so sure what was going on in North Dakota. I mean, the chloride is with regards to water relations. I mean, they don't give you salty popcorn in a bar because they're worried about your corn deficiency, right? They want you to retain more water. And the chloride helps the plants retain water. We saw earlier heading, maybe a day longer of grain fill. And we also could measure a reduction in a root disease quite routinely. Now, those aren't the things that give you huge yield increases. A plumper grain, maybe a reduction of a low-level disease. You're talking 5-10% yield response. Now, Rick Engel in Montana, they had full-blown chloride deficiencies. They were able to get 10, 20 bushels of wheat difference. For me, it was more about water relations and disease resistance, and a little earlier heading, a little long, maybe a day and a half longer of grain fill.
So like if you're someone that's really trying to push small grain yields and you don't have that critical level of 40 pounds of chloride in your 2-foot profile, chloride is definitely something that you want to add to maximize those yields.
Yeah, and of your fertilizer elements, it's probably one of the cheapest ones to add to.
Oh, that's a great point. It's an economic micronutrient.
Yeah. You mentioned this earlier, but when you talked about going to school where you could find that intersection of all of the sciences, and we haven't talked a lot about this, but I know that you've thought about the biology in the soil quite a bit. And I can remember you developing some labs for Soils 210 around like mycorrhizae and things like that. And so I'm going to lob up a really open and very general question for you to just have fun with. When you think about soil microbiology, just what do you think about, or what are your favorite parts of soil microbiology?
Oh, boy. Yeah, I mean, I know that's probably the one aspect of soil science that's probably going to change the most, just because the tools are so advanced. I had as good a training in soil microbiology as could have been had. I had it from Dr. Pengra at South Dakota State, one of the most beloved professors that ever was on that campus. And, we plated, we did all of these chemical tests to try and identify various things. Well, now they send the sample away and they can test, because of DNA, they can test for thousands of different types of organisms in the soil. For example, right now I'm on the graduate committee of a student in microbiology, and we're studying IDC. And she's studying the rhizosphere of susceptible varieties, resistant varieties, with and without soy green. She's looking at the components of, what organisms are the soil, are the plants favoring and promoting? And how is the IDC making the plants change the microbiology of the rhizosphere? We couldn't do any of that back in the day. Yeah, we couldn't do any of it to that degree. And right now, it's such an information overload. It's such an information overload. And, the eternal Lutheran question is, what does this mean?
I think it's kind of the same struggle that parts of precision agriculture also face too, right? Like when we think about doing these big DNA screens and all of a sudden it's like, okay, we've got these thousands of microbiology or microorganisms that are living here, it then becomes a question of, okay, we know it's here, but what does that mean? I mean, we're also missing the disease triangle these aren't necessarily causing disease, but do we know if its presence actually means that it's doing something? Yes. And same thing with like precision ag and big data, right? We're collecting a lot of information, but sometimes it can be hard to condense it and turn it into something that we can use and make meaningful.
Yes, I know. We're able to collect information about these organisms in the soil. And again, what does it mean? And how do we harness it? How do we exploit it? Okay, so the plant undergoes IDC. The plant favors a new population of organisms. Which one of those do we isolate and use as an inoculant to help alleviate the IDC?
Just going back to the day of thinking about iron chlorosis in the rhizosphere, I can remember reading some of Lindsay's research where he had shown that the rhizosphere of a soybean plant has the ability to lower the soil pH by 1 whole pH unit. That's huge. That's something that humans can't figure out how to do. But yet that's only the chemistry portion of it. We're not even scratching the surface at the biology within there. And so my questions in my mind when we start thinking about soil biology and the rhizosphere immediately go to, okay, so if we've got iron chlorosis going on in this area, not only what sorts of organisms are going on, but if you've got that acidification going on in that rhizosphere, what is that doing to the soil biology? And how is that complementing or making things more challenging for the soil biology? It seems like it's such a place where we are just learning so much about what's there, and it's going to be just so fun to see what's going to happen.
Yeah, and there will be false starts, right? There'll be false starts where we'll think that something's happening, but we can't prove it out. And also the soybean root not only can acidify, but also can release reducing agents. There's only 3 ways to make soil iron more available. There's acidification, there's reduction, and there's chelation. Those are the 3 ways. And the chelation can go both ways. I mean, we talk a lot about the siderophores that plants can give off or microbes can put out. Well, sometimes when a microbe produces an iron siderophore, it's not to make iron more available. It's to starve their neighbor of iron,
What is a siderophore?
It's basically a type of chelate or something that binds up iron. And it's often thought that, siderophores are good. They take up iron, and then when those are decomposed, they can make iron available. But they're basically, they're a form of chelation. It's a form of tying up iron into an organic compound.
So is it kind of like when you're playing Mario Kart and you don't want your competitor to beat you, you throw a turtle shell at it and it binds to their tire and they can't move?
I'm game to try.
But it's like a competitive chelation where
it's a competitive thing, yeah. And sometimes it's to make iron more available, but sometimes the siderophores make iron less available, at least in the short term.
Oh my gosh, that's so cool.
Yeah, you have to think of the soil microbiome as a war.
That's really fun.
It is a war. I mean, those organisms are competing for everything, and there's a lot of them.
I love that. And this is a good place, I think, to stop the first part of our discussion here with Dr. Goos. And I think what we'll probably pick up on next week is continuing discussion of what this soil looks like at the soil level, but also more of the science of IDC too. And what are the things that we do for sure know that we can do a better job of applying some of these precision agriculture concepts, VRT, et cetera, to better manage IDC. But it has been an awesome conversation geeking out about soil science with Dr. Goos for the last half hour. And
I can't wait to geek out again.
Yes. Please join us in our next episode to do more of the same. But with that, thank you guys so much for listening. And Remember, with GK Technology, we have a map
And an app
for that.
And I can't wait to get in the fields again. No, I can't wait to get in the fields again.
Let the geeks at GK Technology help you with your agricultural data. Their agronomists know agriculture. When it comes to creating soils and zone maps to maximize yields in your fields, you can trust the people with decades of experience in site-specific agriculture. Everyone at GK Technology has a background in agriculture, so they know what makes a farm run, and they speak your language. The geeks at GK Technology have a map and an app for that.